Morning, welcome to NGSS Physics. We are going to be going over some kinematics today. So make sure your slideshow and your guided note slide is up and running so that you can take some guided notes. Kinematics is our subject topic of discussion. This is the study of motion in one dimension. If you take a look at the CK12 physics book, and there is a link in your syllabus, this is section 2.4 to 2.6. So if you want more information on kinematics, 2.4 to 2.6. Kinematics is the branch of physics that studies motion. So that's what we're going to be doing today. And two very important definitions we've already gone over. One is distance. Distance is the length of a path traveled, regardless of direction. You can change direction, it doesn't matter. How far did something go or move? That is the distance. And we usually give distance, we use d to represent the distance. Okay, we'll use this d right there. The other thing we went over already was displacement. Now this one does depend on direction, and we use an X to mark the spot for displacement because it's really all about where something is placed and where did it start, its placement, and where was its placement when it ended, and what is the magnitude between those 2 points and the direction. And so sometimes distance and displacement can be the same thing, but sometimes it is not. Displacement depends on direction. So we've already gone over these vocabulary terms. If you're having trouble remembering them, I highly recommend making some flashcards of some of the vocabulary and then building a flashcard deck for your physics classroom. Okay, let's go over this in graphic form here. Let's say you're in a car and you travel along this red line. Well, your odometer is going to click off in your car, and it's going to tell you how far that your car has rolled. And let's say it says it rolled 8 miles to get from the start to the finish. That is the distance. But the displacement is basically where did you start versus where did you end up. And so that's going to be the green arrow. And you can see the magnitude is going to be different between distance and displacement here. Not only do we have a shorter magnitude for our displacement, but we also have a direction involved. It looks like it went off there to the east. What if you drove in a circle? Well, you definitely will have a distance that you drive, and that would be equal to the circumference of the circle. But the displacement might be zero if you started and ended at the same spot. So that's a review from last week. If you still are having trouble with them, you need to look them up, put them on a flashcard, and make sure that you remember them. Okay, today we're going to go over acceleration. We're going to add this to our other formulas. So far we've had speed and we had velocity. Speed is how fast you're going. And we said that speed, okay, was equal to the distance over time. So that's one formula that we've already had. We said velocity is not necessarily how fast you're traveling, but this is how fast in which way. In other words, the rate at which displacement occurs. So velocity we were given as the change in displacement over time. And sometimes if there was no change in direction at all, they could end up being the same number, the same magnitude number, okay, with just an added direction for velocity. Acceleration is how fast you speed up or slow down or change direction. Well, if you speed up, slow down, or change direction, then what you're really changing is your velocity. So acceleration is the rate at which velocity changes over time. And I can write, something that looks like this. And I'll give you this formula a little bit later as well. Okay? All right. Here's a couple of other vocabulary terms I'd like you to know. I'd like you to know, what does a scalar quantity represent? And this is one that doesn't consider direction. Okay? For instance, when you're driving, you usually look at your speed on your speedometer, and it doesn't tell you a direction, it just tells you the magnitude, 20 miles per hour. Okay? This is different than something like velocity, which is a vector quantity. And a vector quantity is one that has both a magnitude and direction. Okay, so you have to add direction in there, not just a number that shows how much, but which direction you're going as well. Okay, so velocity is a vector. And it's a vector because the displacement is a vector. There's direction to it. And because acceleration is the change in velocity, we're going to find out that acceleration is also a vector. It's got direction. Okay, here's a quick question. You might want to write down those formulas. Okay, speed is distance over time, and velocity is the change in displacement over time. Okay, so if we have those formulas up there, it's easy to see that the one with the bigger direction, or distance, sorry, the one with the bigger distance is going to be going the greater speed. And it looks like the blue car, basically this path looks like a bigger number than the orange path. So the blue car has a greater speed, okay? Blue. Okay. On the other hand, B, which has the greatest velocity, because velocity is dependent on placement. Well, X marks a spot here and there, exactly the same spots. They're going to have the exact same displacement. So therefore, which one has the greatest velocity? They both have the same velocity. Okay, so it's the same here. Okay, because the displacement was the same. So please be careful when you see questions like this. Sometimes they look like, they could be kind of tricky. Okay, here's a concept question using a stroboscope type thing, where we have maybe a ticker tape going through a machine, taking or writing dots continuously, evenly spaced over a different time. So we'll just pretend like it's drawing a dot every second. And this is for us to visualize speed. How would we visualize speed then? Well, let's take a look at this. If these dots were drawn every single second, what would it look like as something was traveling through our stroboscope? Number one, which of the above indicate a constant velocity? I'm expecting the same amount of space between the dots for constant velocity. So I am thinking maybe A and maybe E. So A and E, same amount of space between each of the dots. They have a constant velocity. Number two, which is speeding up. Here, I would expect more space between the dots as time goes by because it's speeding up. It's getting faster and faster. So probably C. You can see that the dots get bigger, get more spread out. Well, that means that slowing down, it would be the exact opposite. You would get those dots kind of squinching together, something like that. What's going on with D here? It looks like in D, it's going kind of slow, and then it speeds up and goes kind of fast, and it gets kind of slow again. So it speeds up and then slows back down. All right, so let's putting it together with our vectors, because velocity and acceleration are both vectors. It can get confusing when you have one as a positive vector and the other as a negative vector. What's really going on? So let's just pretend like we have a car, okay? And let's pretend like the velocity of the car right here is the car is moving forward, just like that, okay? And here we'll pretend like the car is moving backwards, so it's backing up. So here it's going in the forward direction, there it's going in the backward position, okay? So if you have a forward moving car and the vector for acceleration, okay, that force that gets it to accelerate is also in the positive direction, then you're probably going to expect it to speed up. This is different than if you have a forward moving car but has an acceleration in the negative direction, okay? If that happens, you'll probably expect it to slow down. Now let's take a look at the backward moving car. So let's say the car is moving backwards, but you have a positive acceleration going in this direction. Well, I'm going to expect the car that's going backwards, it's still going backwards, but it's going to slow down as it's going backwards. Okay? here, car going in the backwards direction, and also has an acceleration in the backwards direction. It's probably going to speed up going backwards. And I know those lines kind of confusing. Okay, so that's what's going on there. Here are some graphic forms. What if you have a positive acceleration and a positive velocity? Well, the positive velocity is here. Here's velocity. Here's the positive velocity up here. With a positive acceleration for my velocity, I'd expect it all to be in the positive sector of the graph. As opposed to a positive velocity, here's positive velocity here, but now we have a negative acceleration. So now it's going to point downward, but it's still in the positive section of the graph because it's positive velocity. Over here, we've got negative velocity, and so we're going to expect it all in the negative section of the graph, up there and down at the bottom, okay? The first one has a positive acceleration. So anytime you have a positive acceleration, it's going to point up. Anytime you have a negative acceleration, the vector is going to point down. And so that's how you can read those graphs. That's what we would expect in graphic form. If you can recall in our lab last week, I asked you to try to predict what would happen if you had constant velocity. And in that case, it was a straight line going straight across because there was no acceleration. But with an acceleration, we're going to expect a slope. Okay, here are the formulas. Acceleration is the change in velocity over time. So we can write it out like this. The final velocity minus the initial velocity divided by time, or we could just use the delta symbol, that little triangle, delta V divided by T. That delta just means the change in something. Okay, remember, with velocity, we also had that delta down here, which is the change in displacement over time. So that's all that means, that a change is going on. Look at that, my writing. That means a change is going on. So a change in velocity or a change in position, depending on which formula you're looking at. You should know all three of these formulas. If you didn't print out the formula sheet, write them down on a separate sheet of paper. Make your own formula sheet if you need to, little by little, as we get all of the kinematic formulas. Let's take a look at an example. A ball rolls down a ramp for 10 seconds. If the initial velocity the ball is 0.9 meters per second, and the final velocity is 6 meters per second. What is the acceleration? So the acceleration, okay, we have as the change in velocity over time. Okay, so I'm going to put the final velocity, here it is right here, 6, the initial velocity, and 10 seconds. Okay, those are all the numbers in there. So the first thing I want to do is figure out what is 10. 10 seconds, that's a time, okay? That's time. What is the 9 meters per second? And it says it was the initial velocity. What is the 6 meters per second? That was the final velocity. So that delta really means the final minus the initial over time. So what I'm going to have here is the final velocity, which is 6, minus the initial velocity, which is 0.9, over time, which is 10. And notice that these are meters and these are seconds down here. Velocity is meters per second. So my units are going to be meters per second squared. That's what's going to happen. And I end up with 0.51. Make sure you try these on your calculator so that you can make sure that you could do these as well. Okay, a car is going 45 meters per second. What is 45 meters per second? That looks like it's a velocity. And it accelerates to pass a truck. 4 seconds later, that is my time. Okay, 4 seconds. The car is going 70 meters per second. Okay, calculate the acceleration of the car. So this is also a V. So it looks like this is the initial velocity, okay? And this is the final velocity right there. So we want to calculate the acceleration, which is the final velocity. minus the initial velocity, all divided by time. That's the formula. Write it down if you don't have it written down so that you will no longer be saying, where do I get the formula? Okay, the final velocity is 70 meters per second minus 45 meters per second divided by 4 seconds. I am going to get some kind of units in meters per second, or meters per second squared, which is the units for acceleration. And 70 minus 45 divided by 4, put those in my calculator, I get 6.25 meters per second squared. All right, here's our summary. A vector has magnitude and direction. Both velocity and acceleration are vectors, as well as displacement. Acceleration can be either a change in the magnitude or the direction of a vector. One of those two changes, you just changed the velocity, and therefore you have an acceleration. All right, we'll see you back in class. Good luck filling out that